post this on YouTube.
Excellent. Thank you very much. That's appreciated because I think I got that. I think most of it makes like pretty clear sense, but might need to go through and watch that again, you know?
Yes, I think in my MATLAB code, I use the matrix multiplication. So make sure you check it line by line, make sure you understand what's going on over there. All right, so I think the MATLAB code is going to be really helpful. So up to this point, as you can see here, this method is the eigenvalue and eigenvector. So one thing I already explained how to calculate eigenvalue and eigenvector. Perhaps I can give you an example later. So beyond that, so using the state space representation or convert everything to Y domain, that's the most common method you're going to use if you want to learn electrical engineering. But in mechanical engineering, so we still need to solve this ODE in the second order domain or in the X domain. The reason why is the natural frequency and mode shape, because a lot of information of the mechanics system is hidden in these two concepts. We're going to explain what they are in this class. So first of all, let's recall what we learned at the very beginning of this class, I think in lecture number 2. We have a single degree of freedom system. Basically, you have a mass sitting on a spring. And then we only need one coordinate to describe the vibration of the system. And this is free vibration, so no force applied, only subject to initial conditions. So we can easily find these ODE. And then to solve these ODE, the first thing we did is we assume that our solution is in this format. So it's a very interesting assumption or hypothesis. So just by looking at these equations, we guess how this solution would look like. So from our own experience, we know that the system is going to oscillate harmonically. So that's why we assume your response is a harmonic equation. So what we do is we plug in these assumptions back into your ODE. Then you have x double dot equals to a e j omega t. And then we need to multiply it by j omega squared. So that is minus omega squared a e j omega t. And then your x is a e j omega t. And then you plug all the coefficients in. Plus k a e j omega t equal to 0. So once we plug it back in, so this is the actual assumption. We assume the solution is in this format. And then this equation, that means these ODE should always be true no matter what your time point is. So that means at any time t, your ODE is true. Otherwise, it violates this Newton's second law. So that means this equation is true for any time for any time. So that means to satisfy this red condition, we have to make sure this is true. And then that's how we get omega equals to k over m. And then we name this omega as omega n, or resonance. All right. And then actually you can find two omega. One is, yes, actually, yep. So once you find the omega, then based on the assumption of our solution, then we have xt equals to a1 ej omega nt plus a2 minus j omega nt. So that's how we find the solution of your ODE. So A1 and A2, we have two unknowns. So these A1 and A2, they're constants. They're determined by your initial conditions. Two equations, two unknowns. And then we also assume that your xt can be written as A sine omega nt plus phi 1. So these phi 1 and A, they are constants to be determined. They can be calculated from initial conditions. So that's the idea when you have first order systems. All right, so let's go back to our very beginning of these methods. Let's go back to these assumptions. This is actually a very interesting assumption. So I don't know who's the first finding these assumptions, but you might be wondering why we assume the solution in this format. Because there are infinite number of equations in the world, so why they pick this one? So this actually is a very important concept. It's called variable separation. So in this case, oops. For a system like this, you have both position x. You also have the time variable t. So that's why you actually have two variables in your system. And then in order to solve a system with two variables, we assume that our assumption is something is a part A. Why should we use another one? Part 1 times part 2. So your part 2 is only a function of time. And your part 1 is only a function of x. So we separate these two variables. So in this case, your part 1 is actually a constant. That's very special. The second one is a harmonic excitation. So by using different part 2, you might have different expressions. And in mechanical systems, we usually assume harmonic excitation because of the Fourier series. So any periodic signal can be decomposed into harmonic oscillation. And if you work in magnetics, they actually have other kind of part 2 assumptions. You can sometimes they have those, the so-called Bessel function. If you work in magnetics, so instead of using harmonics, you're going to use another type of function, which is the basis of your solution. All right. So that's for a single degree of freedom systems. So if we move on to our multiple degree of freedom systems, you can do something really similar. What you can do is we assume that your xt, we need to assume it has two parts. The first part is, let's name it as u vector. So this one is only related to coordinate x. And then the second part is ej omega t, is only a time-dependent function. And because it's mechanical, we assume a harmonic response. So that's time, that's coordinate. All right. So then the next question is, how can we find u and ej omega t? So very similar to the first degree of freedom method, we just calculate your xt double dot. So the benefits for variable separation occurs in here. So if you want to calculate time derivatives, that means your first term has nothing to do with time because we already separate these two variables. So the first one you can consider as constant, and then you just need to calculate time derivatives for the second term. So j omega squared e j omega t. And then you have minus omega squared u e j omega t. So that's why separating these two variables are very valuable, because once they're separated, you can easily calculate the time derivatives. All right, so let's see what we have here. Mx dot plus kx equal to 0. So that's not convenient. So let's change it to m to x double dot plus m invert k x equal to 0. We just multiply both sides by m inverse. Then we have these. And then for convenience, let's define what's underneath here is d. So what is the D matrix? The D matrix is just positive m inverse times k. All right. So we already know your x double dot is minus omega squared u e j omega t times d times your u times e j omega t equal to 0. So from here to here, we just plug in x and x double dot. The same thing, this equation is true at any time point t. So that means we should have omega n minus, oops. You have to multiply everything by identity matrix, otherwise your matrix will dimension will match. We just make sure this is always 0. So if you don't understand this, then we have to go back to the linear algebra a little bit. So if you have a bunch of, let me see. If you have n linear equations, and these linear equations can be written as A, U equals to 0, and then U is n by 1. So U1, U2, and UN, they are unknowns. So that means if your nth order linear equation has non-zero solutions of U, that means this can only happen when the determinant of your A matrix is 0. So in linear algebra, we call your A matrix is not full rank. So if you haven't taken any linear algebra class, so that means the only thing you need to remember here is if you have, we call these homogeneous equations, that means the right-hand side is always 0. If a homogeneous linear equation have non-zero solutions, your A matrix cannot be full rank, or your determinant, the determinant of your A should be 0. So let's look at it here. So if you look at the original equation, it can actually be written as times U have to be 0, right? So as I said, this is true, Ej omega t. So this equation is true for any time point t. So that means these underlined parts can be non-zero. So that means for these equations, you can find non-zero solutions. So this is true, only the determinant of the part in the bracket is 0. All right, so that's why we have to solve these equations to find the omega. And if you compare this equation with eigenvalue definition, let's say find eigenvalues of matrix D. As I said, in order to find your eigenvalues, you need to solve lambda I minus D equal to 0, right? If you want to switch signs, it's also equivalent to minus lambda I plus D equal to 0. And then you compare these two equations. They're actually the same thing. So that means your omega square is lambda. So this lengthy mathematical derivation, the conclusion is actually here. So when we decouple your solution, we separate the variables into coordinates and time functions. For the time function, the only unknown is your omega. So the way we find omega is actually from eigenvalues. Your omega is the square root of your eigenvalues. Make sense? So perhaps I should write these down. Conclusion number 1. Conclusions. So remember, your solution can be written as U times Ej omega t. Conclusion 1 is omega squared is lambda, and then lambda is eigenvalues of D. And then remember, your D is M inverse times K. So that's for matrix format. So if you have a scalar, if your D is a scalar, then your lambda is just square root of K over M. You can see that how they match each other. But then if you have matrix format, your eigenvalues is actually the eigenvalue. Your lambda is your natural frequency is actually the eigenvalues of these matrix. So that means in this case, if you have, depending on how many masses you have in your system, you might have more than one natural frequency. So if you have one mass, you have one natural frequency. Two mass, you have two natural frequency. So these can be expanded to infinite number of masses. For example, if you take future classes for continuous vibration, so in those scenarios, we actually assume that a structure is consists of infinite number of masses. So in that case, we actually have infinite number of natural frequencies. All right. So the second conclusion is your U vector is eigenvectors of lambda. You can easily see here from this equation. Let's go back to this equation. So again, remember that your minus omega square identity matrix minus D times U should be 0, right? And remember that your omega squared minus, that's already replaced by lambda. Is that you? Oops. Yes. I should put it in a different way. So that's your omega square. Yep. So these has been replaced by lambda. So lambda I minus d times u equal to 0. If you forget the definition, that's actually the way, the equation we use to calculate eigenvalues or eigenvectors. All right. So here, by solving these, you can actually get, because we have two lambdas, then we have two eigenvectors. If you have two lambdas, you have two eigenvectors. You have n lambdas. You're going to have n eigenvectors. All right. So remember, here we see two very important definitions. Your omega are natural frequency. Your omegas natural frequencies, and I is from 1 all the way to n. And then your UI, we call it mode shapes, and I is from 1 to n. So that's the definition. So what is mode shape? So let's use a simple system, for example. That's your x1. Or I should use another one, which is more clear. So if you have a ball, M1, M2, and then they're connected by three strings. All right. So as you can see here, it acts. So let's ignore the mass of the wires. So because there are two mass, we're expecting two natural frequencies, and then we're also expecting two mode shapes. The mode shapes would be, let's say omega 1 is smaller than omega 2, then you're going to see your U1 will be something like this. And then your U2 so what is U? So let's say we use a coordinate x1 to describe the position of M2, M1, and then we use a coordinate x2. So your U1 will be U11, U12. So that means, what's the meaning of your U1? That mode shape. That means when your system is operating, when system is at omega 1. Let's say you're shaking these two balls, and when your shaking frequency is at omega 1, then your response would be U1. We're in the shape of U1. And then how to describe the shape? So this distance is U11, this distance is U12. All right, similarly, if your system is at omega 2, that means your system will, your response will be described by U2, which is U21, U22. So So this distance is U21, and this distance is U22. So the mode shapes gives you an idea how the system will look like when it vibrates at that frequency. That's when you have two balls in the system. I believe if you go to YouTube, I can share you this video later. I think there is a video from Penn State University. They actually run a huge experiment in front of their mechanical engineering building. You can actually visualize these two modes as those natural frequencies. So that's the mode shape. The other way, actually, if you're home right now, you can actually see one of the popular mode shapes. If you have if you have a ruler, you can easily clamp one side, create a cantilever beam, and then you apply an impulse to the tip. And you're gonna see these beam vibrates like these, right? Just going back and forth between these two positions. And then, let me use the red color. So the vibration speed is actually the first resonance of the cantilever beam. And then the red line describes the mode shape of the first mode, which corresponds to the first natural frequency. So that's why mode shape is very important. So so it actually gives you a basic idea about how your system will respond to an impulse excitation. All right, it might be really hard to understand natural frequency here. Let's use an example. Perhaps this would be a better example, right? So we have a system. We already seen this system for at so many different places. We find your MK positions. So in order to find, so the first part is find natural frequencies. And mode shapes. So what are natural frequencies and mode shapes? That's basically the eigenvalue problem. So the first thing you need to do is you need to find out the D matrix. The D matrix is just M invert times K. And then your M is 9, 1, 0, 0. Your K is 27, minus 3, minus 3, and 3. That's invert. Eventually, that gives you, let me see. So the D matrix is 3 minus 1/3 minus 3 and 3. So in order to find natural frequency, you need to find out your lambda of A, of D matrix. To find lambda of D matrix, if that is just, remember it's P and lambda. So all the lambda are diagonal terms in lambda matrix here. All right, so let's look at here. So when you plug it in, if you want to solve it by hand, it's actually lambda times identity matrix minus D. We want to calculate the determinant equal to 0. And then what is lambda? So the first matrix is lambda, lambda, 0, 0. The second matrix is 3, minus 1/3, minus 3, and 3. The determinant is just lambda minus 3, 1/3, 3 lambda minus 3, and then equals to lambda square minus plus 8, and then you can factorize it. It's lambda minus 4 equals 0. So then you can find lambda 1 equals to 2 and lambda 2 equals to 4. If you forget how to calculate determinant, in MATLAB it's just DET, whatever matrix you put in. If it's only two-dimensional, you just can't multiply these two terms and minus the multiplication of these two terms. But if it's three-dimensional, even higher order, then it becomes complicated. I suggest you to use the DET function. So if you have lambda 2 and lambda 1, then you will know that your first natural frequency is square root of lambda 1. The second natural frequency is the square root of lambda 2. So you find the two resonance of your system. All right, so the second part is what are the mode shapes? So the mode shape is just eigenvalue of D. So again, if you want to use the eigenfunction in MATLAB, you find all your U from the P. So your P matrix will be U1, U2, and UN. So that means in this case, your P will be, you just find the, in order to find your U1, you just write your P matrix out and pick the first column. That's your U1. And then similarly, your second column in P is going to be your U2. If you want to solve all of these by hand, you just plug in, you just need to solve these equations. And then you actually have to solve these equations n times. So here, for each lambda, you have to solve it once. So your lambda 1 is square root of 2. Oh, sorry, your lambda 1 is 2. In this case, we have natural frequency omega 1 equal to square root of 2. And then you have to solve the equation. If it's 2, then it's minus 1. 1/3, 3 minus 1. You have U1 equal to 0, 0. So what is your U1? You can see that your U1 is actually, there is no unique solution for U1. There are actually more than one solution. In this case, that's one solution. Your C0 is just a constant. So as long as it's C0 times these, you're going to have a one solution. So that means your eigenvector is not a unique vector. It's actually a group of vectors. All right, similarly, you can plug in lambda 2 equals to 4. Oh, I think I had a typo here. And then you have omega 2 equals to 2. And then in this case, you just plug lambda back in. You have 1, 1/3, 3, and 1. You have U2, 0, 0. And then your U2 again, same thing, minus 1/3 and 1. So C1. Let's try to avoid confusion. Your C2 is also a constant. So that's how you calculate everything by hand. So these box parties calculate everything by hand is equivalent to these MATLAB code. So you have the freedom to pick which one you like.
So I would assume that the MATLAB code is a lot easier.
Oh yes, definitely. Like if you have, for example, in the final program, it's going to be usually. So yeah, please learn how to use eigen EIG function. All right, so that's why we have your natural frequency. We have the Moshe. Well, the problem here is, what's the time domain response for X1 and X2? Here we only know natural frequency and Moshe. How can we derive the time domain response, the final solution we want? So before doing so, let's recall properties of eigenvectors. So there are two very important properties for eigenvectors. Did I have it right? Perhaps I don't have time to go into this. Let me directly. What's the best way to present it? Anyway, so once you have Moshe and natural frequency, how can you go back and construct your solution? So what you do is you collect all the solutions in a column vector like this. And then very similar to the single degree of freedom problem, you have your X equals to, let's go back to the single degree of freedom here. So in the end, you have option number 1 or option number 2. You can either use Euler's expression or you can use harmonic excitation to describe your final solution. All right. So then you also similarly, you also have two potential methods to describe your XC. So option 1, Euler's expression. So your X will be A E J omega E T plus B E J minus E J omega 1 T U1 plus C E J omega 2 T plus B minus E minus J omega 2 T U2. So for each natural frequency and Moshe, you have one expression. And you have two unknowns, A, B, C, and D. In total, you have A, B, C, and D, 4 unknowns. And then remember that you have X1 not, X2 not, X1 dot, X2 dot. So for each initial velocities and for each initial conditions, you get one equation. You have 4 equations in total, 4 constants to be determined. That's how you find A, B, C, and D. So if you don't like this Euler's expression, you can also use option number 2. Your xt would equals to A1 sine omega 1 t plus phi 1 U1 plus A2 sine omega 2 t plus phi 2 U2. So in this case, the unknowns, they're A1, phi 1, A2, phi 2. Again, you can find them from the 4 equations related to your initial conditions. So here's another way to visualize your mode shape. Your mode shape is, they're actually building blocks of your final time domain solution. As you can see here, eventually your final solution can be a summation of different modes. I don't have a preference. No. Personally, if you want to use MATLAB, I think the OLS expression is easier. Because if you want to solve these phi 1, phi 2, remember that in previous lecture we said, eventually you need to pick, there was 2 solutions for phi 1 and phi 2. You need to pick the correct one based on the signs. So it's going to be complicated. I think, especially for MATLAB coding, I think OLS expression option 1 would be easier for MATLAB coding. But then the drawback is you don't see the sign as cosines directly. You're seeing exponential terms. So if you look at these expressions, these time domain solution here, one thing we learned is the free vibration of a multi-degree of freedom system, they're going to vibrate in 2 frequencies. If you excite it, so sometimes, depending on your excitation, sometimes the first mode have a higher weight, or sometimes the second mode has the highest weight. If your excitation is in the sweet spot, you would selectively excite the first mode or the second mode. So that's actually an important thing for later vibration control. How can we experimentally find out the mode shapes? You have to pick the impact hammer again and then just hit it in a different way. So that's for a second order system. So if you recall, a first DOF system or single DOF system in lecture 2. The solution is no longer a vector, is a scalar, right? So that's the solution for a single degree of freedom system from lecture 2. So as you can see here, the mode shape is actually 1, is a constant 1. So that's special. All right, I think this class is too much on math. I think the first thing I will do is I will find a nice PDF file that review, perhaps a review on eigenvalues and eigenvectors. You can check it out. And next lecture, I'm gonna go over some examples in details. So we're gonna forget about these math problems, directly run into how we solve it. Right? Yes, that's just the background. If you understand these, then you know why the world is operating this way. But then as I said, as an engineer, sometimes you just need to know how to make it work. So perhaps next lecture is going to be about the how part. All right.